you just want to stay in here, or you want to turn it over?
All right, well, next up is Rahul, and he is single-handedly responsible for making everything in the department smell like garlic. The extraction processes are speed back, the lab, the walls, and it is permeating everything. To the point that our custodian would not go in the room after a while because she absolutely hates the smell of garlic. But he actually has a really interesting project, and this is a cool thing. I'll let you tell more about it in terms of the actual process. But this was a lot of fun. He got to smash a lot of things. We got to do some pretty complex chemical extractions and things like that, and then test susceptibility. So it was an interesting project. Please take it away.
Okay. So my project is called an in vitro study on bacterial susceptibility and resistance to allicin. So I'm going to be talking about an antibacterial compound in garlic called allicin. But before I do, I'd like to give a brief history about garlic in general. So garlic was used as a panacea by many civilizations. Panacea is kind of like a cure-all. For example, the Chinese used it as an antidepressant. The Indians used it as a anti-rheumatic arthritis and things like that. And the Egyptians used it for strength, kind of like steroids. But most interestingly, the Israelites used it as an anti-parasitic, like almost 2,000 years ago. And I find this very interesting because this is very similar to the research that I'm doing right now. So the fact that they were doing it that long ago and it's still being done today is a pretty big deal. So even Louis Pasteur, and I think everyone knows who Louis Pasteur is, he described the antiseptic qualities of garlic in 1858. And no one knew why allicin was antiseptic or antibacterial. They just knew it was, but they didn't know why. But since then, it is found that a particular compound called allicin was responsible for the antibacterial efficacy. So what is allicin? And why does it act like it does? So allicin is an organosulfur compound found in garlic. So if you chop a piece of garlic, you're going to get some allicin. It's very biologically active. So biologically active means that it either has a positive health effect or a negative health effect. And in this case, it has a very, very positive health effect. And it exists only to protect garlic from bacterial and fungal attacks. And it's only activated when the skin is penetrated or destroyed. So it's a basic protection mechanism that has evolved over millions of years. And it's unwittingly helping us kill bacteria now. So that's pretty interesting. So the medicinal qualities of allicin come from its formation. So I'm going to talk about that. So there's this amino acid in garlic called allicin. And what allicin is whenever you chop a piece of garlic or smell it, allicin is the most common amino acid found in garlic. So what happens is there's this enzyme called allinase that's activated when you chop or destroy a piece of garlic. After that enzyme is activated, it converts allicin to allicin, and that's what we need. So extracting this is a pretty difficult procedure because allicin is a very volatile compound, and in maybe 2 minutes it can just dissipate and go away. So, and it's also very effective against antibiotic-resistant diseases like MRSA. As you can see in this picture, this patient was on antibiotics for 4 weeks, nothing happened. She was on really, really strong antibiotics that were taking a toll on her health. She was also on intravenous vitamins, which did not have any effect at all. So she quit all her antibiotics and she went to a doctor, and the doctor decided to test out. It was never done before. And she took allicin capsules every day. She poured allicin liquid in her drinks, and she applied allicin cream to the wound on her face. And in 3 weeks, it went from here to here to here, and her MRSA infection was, almost all of it was killed. So, I mean, I don't know if I believe all of it, but it's pretty convincing. So what were the goals of my experiment? So my goal was to examine the antibacterial efficacy of allicin against 5 types of bacteria: Pseudomonas, Klebsiella pneumoniae, Staphylococcus, Salmonella, and E. coli. And I chose these bacteria because they're very pathogenic to humans and they're very commonly found around the human body. And I postulated that allicin would have an effect on all of these types of bacteria, but that it would also be very, very effective against Staph aureus because it's been done in the past. So my second goal was to ascertain whether a specific bacterial species can undergo mutagenesis, become resistant to allicin. And this has never been done before. I looked through papers, I couldn't find anything. So I made a postulation that it would undergo mutagenesis. But first I had to extract the allicin. So what I did was I got fresh garlic, thanks to Ian, who's not here, but he went to the supermarket and got me some garlic. So I got a mortar and pestle, and I jammed it for about, I think, almost an hour. It was very tiring. Soon I developed this garlic paste. It was like pasty consistency. So then what I did, I poured methanol, or ethanol, on top of it to fill it. And I let it sit there for about an hour to dissolve all the allicin into the methanol and only leave garlic residue behind. Then what I did is, it's a very tedious process, but I poured the liquid into 24 different microtubes, centrifuged it with the lids open to promote evaporation. Then I rehydrated it all again, centrifuged it again, did the same thing over and over and over again until I ran out of the liquid. And then I developed this very, very concentrated thing, or a very, very concentrated tube of allicin, or 24 of them. I transferred them all into one big tube, and we put them in the super vac to develop a solid extract. Then that solid extract was rehydrated, and that was the allicin that I wanted. That was what I was looking for. So then we did thin layer chromatography, which was pretty fun. I'd never done it before. So this is the chamber that I use. I use ethyl acetate and isopropanol as my agents. So what I had to do, I used a pipette to drop 4 drops of my allicin extract onto the plate, and I put them in my chamber. And then I waited about half an hour, and soon there's a large area of separation between the original drops that I put and a new compound that was formed at the top. And the compound that was formed at the top, as you can see right there, and that was the allicin that I wanted. So what I did, I had to scrape all of them off. I put them into tubes, and they're all in different concentrations, and I have my allicin extract. The next thing I did was I plated my bacteria. I plated all the bacteria, and then I used this diffusion to test the antibacterial efficacy of allicin. So this diffusion is pretty much, you place a wafer disc in the middle of a plate and infuse your agent. In my case, it was allicin. Sometimes, most of the times you use antibiotics. But I put that in the middle, and I let it incubate overnight to see what it looked like in the morning. And this was my Pseudomonas. It was one of the more effective ones. So you can see the zone of inhibition. So the zone of inhibition is where nothing grows. It's where the bacteria is killed by the allicin. And the zones of inhibitions were measured, and I'm going to show you that in my data. And Pseudomonas was the most effective. All the other bacteria were not very effective at all. Then, after I chose Pseudomonas for mutagenesis. So what I did, this is the Pseudomonas sample. This is the allicin, and this is my mutagen. I used hydrogen peroxide as my mutagen. So I infused hydrogen peroxide into the sample disc, and of course let it incubate overnight. Then I extracted colonies that grew in the zone of inhibition, because those colonies are the ones that are resistant to allicin. So as you can see here, I plated and compared the zones of inhibitions between normal Pseudomonas at the top and mutated Pseudomonas at the bottom. And it was pretty interesting. There's a large difference between the mutation and the control, because the mutation was completely resistant to allicin. You can see there's a smaller zone of inhibition. So now to my results. Sadly, my results were inconclusive in the first part about allicin's efficacy against the 5 bacteria. The zones of inhibition are just barely above the sample disk. So for Staph aureus, Salmonella and E. coli, I mean, you couldn't really tell anything from that. But Klebsiella pneumoniae and Pseudomonas were a little bit more effective, but not that effective at all. And I think this is because of procedural error. I might have made mistakes in the beginning when I was extracting the allicin, so maybe it was of a lower purity. So now I'll talk about mutagenesis. This is where I was very, very surprised and very happy because mutagenesis actually did occur. I showed you the picture. As you can see in my control and mutation, that the control, which was unmutated, the zones of inhibitions were so much higher than the mutated version. So I think this is pretty interesting. The Pseudomonas had completely different readings now than in the first part. So because I made the allicin extract again, so I must have done something different this time to get a different result. So it's interesting. And in the future, I'd like to look at the antibiotic resistance, or the use of allicin against antibiotic resistance. Now scientists in China have actually created a new medication that combines allicin with a real antibiotic. So they tested it with a regular antibiotic and this new medication, and this new medication was so much more effective against various types of bacteria than a regular antibiotic. So I think that's pretty interesting. And one thing I want to do, I preserve samples of my mutation and my regular Pseudomonas. I want to look at the genetic structure, see what mutated to cause the resistance. So, and before I end, I'd like to thank the SVSM program, Dr. Anderson, Becca, and Ian. So, thank you.
Do we have questions?